thinking of last week. It just seemed like it was pushing a little bit too much. So we got a lot to go over today. We're going to finish up chapter 4. And we're coming up to this idea called an antiderivative. And what this basically is, it's a function a derivative comes from. So that's the idea of an antiderivative. So for example, if the derivative, well, since the derivative of x squared is 2x, well, this derivative comes from some function, then the antiderivative of 2x is x squared. And let me go back here. Let's not put then an antiderivative of 2x is x squared. And this use of an instead of the is going to become important shortly. Because we're going to find out you can have multiple antiderivatives for the same thing, though what makes those antiderivatives different, it's not going to be as profound as you might think. So because the derivative of the sine of x is cosine x, then an antiderivative of cosine x is sine x. And if you're just joining us, what we're looking at, we're talking about antiderivatives. It's the functions that were derivatives, it's the functions from where derivatives come from. So if you take the derivative of sine x, you get cosine x. So that means the antiderivative of the cosine x. What function did this come from? It came from sine x. And so that's what antiderivative is. And we're saying an antiderivative. Again, we'll talk a little bit about that later. And just another example. You take the derivative of the sine inverse of x. What you'll get is 1 over square root of 1 minus x squared. Then you gotta be careful. And antiderivative of 1 over square root of 1 minus x squared is sine inverse of x. And we want to be careful, the domain here, the domain for x can only go from, oh, not careful, it's not even that. Let me hold off there. And make sure our x is going to be within this interval. So any questions about that? So that's the idea of an antiderivative. We're just asking this question, what function did this derivative come from? All right. So we're going to summarize this, and I'll just summarize what I just said. In general, f of x is an antiderivative of f of x if the derivative of capital F of x is little f of x. Basically, what we're doing is we're reading a chart of derivatives backwards. So any questions about that? Now, let me show you something else. I keep saying an antiderivative instead of the antiderivative. Let's see why that is. It suggests that there might be many antiderivatives for some function. Well, we've seen that the derivative of sine is cosine. So sine of x is an antiderivative of cosine. But likewise, if we took the derivative of sine x plus 5, well, this would be cosine of x. This would be 0. So this would also be cosine x. If we took the derivative of sine of x plus -2, we would still get cosine of x. Again, it's just a constant. In fact, in general, we take the derivative of sine x plus c. This is for any constant. You're going to get cosine of x. So what makes antiderivatives different is whether or not we're adding a constant to our antiderivative. So what does this say? Well, in general, if the derivative of f of x, capital F of x, equals lowercase f of x, then the derivative of capital F of x plus some constant c, this also equals lowercase f of x. So when guessing, put this in quotes, we really don't guess. We just look at our derivative chart backwards. But when guessing the antiderivative of f of x, we write capital F of x plus c. So now we're going to go through those three antiderivatives, the antiderivative for 2x, for cosine x, and for 1 over the square root of minus x squared. So this means the antiderivative of 2x. Before we said it was x squared, because if you take the derivative of x squared, you get 2x. But now we're going to say x squared plus c. And if I'm going too fast, let me know. And the antiderivative of cosine of x. Well, before we said it was the sine of x. And the reason we said that is if you take the derivative of sine x, you get cosine x. But now we're going to say the antiderivative is sine x plus c. And then the same thing with our antiderivative sine inverse. Because you take the derivative of sine inverse, you get the derivative of sine inverse gives you this thing. This comes from sine inverse. So now we're going to say, instead of saying sine inverse, the antiderivative, we say sine inverse plus c. So questions about that? All right. Now, it's going to get tiresome writing antiderivative of. We're going to come up with some slick notation. We're going to write this. Now, why does it take this form? We're going to see this in chapter 5. We're going to use antiderivatives for a specific purpose. And we'll talk about that when we get to chapter 5. But instead of writing antiderivative, we're going to write this. There's a special meaning for dx, a special meaning for this too. But now we're going to go back and do things properly. So now we'll write this, and this is called an indefinite integral. We'll get more into this later. So now we'll say it's x squared plus c. And then the indefinite integral. Here, I'll write that word out here in just a second. We're still calling it antiderivative, but really the term to use, well, I'll stick with antiderivative. I'll stay with it. Let's see, I don't think they switch it on us just yet. They do, so we'll do that. So the indefinite integral 1 minus x squared dx sine inverse of x plus c. And again, we're going to call these indefinite integrals. So if you're just joining us, what we're talking about are antiderivatives or indefinite integrals. And the idea is this: because the derivative of this gives you that, we're basically reversing derivatives. The indefinite integral or antiderivative of 2x is going to be x squared. And for reasons that we went over, if you take this is a constant c is what it is. So if you take the derivative of this whole thing, you'll get this 2x. And it doesn't matter what c is. You can always add a constant to this function. This will be a function in its entirety. If you take the derivative of it, you're always going to get 2x. Same here. This plus a constant, if you take the derivative of it, you get this. This plus the constant, take the derivative, you're going to get this. And so antiderivatives or indefinite integrals, we just reverse this process. Antiderivative of 2x is the function that it came from. Antiderivative of cosine is the function that it came from. Antiderivative of 1 over the square root, 1 minus x squared, it's the function where it came from. And so that's it. We're just reading the derivative chart backwards. But we're recognizing that we could add a constant to any of these functions. And if you take the derivative, you're always going to get this, no matter what that constant was. So dealing with this c, what we're going to be dealing with here, can we sometimes know c? And we actually can. We're getting to what's called a differential equation. And to be honest, this subject of differential equations this is one of the key topics in math, engineering, and science, certainly engineering and science. Differential equations, what are called partial differential equations. This is a huge subject, huge subject. So let's let dy dx be the cosine of x. Find y of x where y of 0 is equal to 7. So again, solving these kinds of problems, they can get incredibly complicated. They can require a lot of creativity, to be honest. And the other thing with them, some of them don't have solutions. And you have to use computers to come up with approximations. So we're going to make this observation. Since the derivative . is cosine of x. So the derivative of what function gives us cosine of x? Well, we find that by taking the antiderivative of the cosine of x. And we'll talk about what this means in chapter 5. And what we've seen so far is that's going to be sine x plus c. It's all right. Now, we have that y of x equals sine x plus c. But we want to find out what c is. So y of 0 is sine of 0 plus c. Or y of 0 is 0 plus c, which is equal to c. Now let's not forget we were told y of 0 is equal to 7. So this means 7, which is y of 0 equals c, or c is equal to 7. So at last, the function we're looking for is going to be this. We've identified c. And we use this is called an initial value problem. We're given a value, a point, 0, 7, and that helps us identify that c. So any questions about that? So this is what's called a differential equation. Very important subject in math and science. Like if you get into general relativity, if you get into quantum mechanics, if you look at waves, if you're studying waves, you're dealing with differential equations, and it's just a really, really neat subject. So we're going to look at an application of differential equations. And of course, it'll be something in physics. Physics and motion. And if you take physics here, or if you take it at another school, you're going to see these equations. So let's recall the displacement function. S of t. Now, displacement is distance that you've traveled, or some distance really that you are from point A to point B. It's really displacement. Like you start here, then you're here at a certain time. If we take the derivative of your location and time, we get the velocity. And then if we take the derivative of velocity, we get acceleration. So what we're going to do, we're going to make an assumption. Assume A of t equals a constant. So we're going to assume a of t is a constant. So this is how we're going to derive our velocity and our displacement function. This is a principle of physics. When you have a displacement function and you take its derivative with respect to time, you get velocity. Take a velocity function, take its derivative with respect to time, you get acceleration. So changing displacement gives you velocity. Changing velocity gives you acceleration. Now we're going to integrate not with respect to x, but with respect to time. And what we're going to get is AT plus C. And the reason is because we take the derivative with respect to time of AT plus C. Remember, A is a constant, T is the variable, C is a constant. We're going to get A. So this means we've reversed the derivative on the velocity. So this means velocity, which is the integral, the reverse of its derivative is AT plus C. So we went from displacement to velocity to acceleration. We do this with the derivatives, but with integrals, we're going to go backwards. So derivatives take us one direction, integrals are taking us to the other. We're going to go backwards. Now what we do is we put 0 in for t. And this would be the velocity at time 0. This is the velocity we're going to have when we start our stopwatch. So it'll be the constant A times 0 plus C, which is 0 plus C, which is just going to be C. And again, if there are any questions about this, let me know. So what we get is V sub 0, sorry, V of 0 is equal to C. So this is what's called an initial velocity. And we relabel this V of 0 as V sub 0. You saw me almost write it. So C will be whatever velocity we have when the stopwatch actually starts. So this means V of t will be AT plus V sub 0. So any questions about that? Excuse me. All right. If I'm going too fast, let me know. So now we're going to find displacement. So to get the displacement, we're going to integrate the velocity So what we're going to do, this is going to be equal to, and this is probably not going to be obvious at all just yet. But the reason it's equal to this is if we take the derivative, what we'll get is AT plus V0. And you can check this if you want. If you take the derivative of this, you'll certainly get that. So any questions? So this is going to be the displacement. Oh, not this. This is our displacement S of t. So this means S of t is 1/2 AT squared plus V0t plus C. Now, once again, we're going to be interested in our displacement, or our location, or a distance, say, from an origin, at some time 0. So the S0 is 1/2 A 0 squared plus V0 times 0. Now, this is a multiplication, not a function of, plus C. This is 0. This is 0. And that's a multiplication in there. So if S of 0 is equal to 0 plus 0 plus C, which is just equal to C. So we have S of 0 is equal to C. And so this we might call initial position, sometimes initial displacement, but we oftentimes call initial position. And we're also going to relabel this. We say S of 0, S sub 0, and that's equal to C. So finally, the formula we get by starting out taking antiderivatives of a constant velocity is A over 2 t squared plus V0t plus S sub 0. Where this is initial velocity, this would be initial position or initial displacement. So any questions about that? All right. So looking at properties, Well, the antiderivative of a constant k times f of x is equal to k times the antiderivative plus c. The antiderivative of negative f of x will be negative antiderivative plus c. And this is a version of this where k is equal to -1. And likewise, if you have the antiderivative of f of x plus or minus g of x will be f of x, capital F of x, antiderivative plus or minus the antiderivative of g plus c. And you can also, so I'll put little dots here because they're individual properties. But there's another way you could summarize this one. The antiderivative of f of x, in parenthesis, the antiderivative of a sum or difference, and this is like with derivatives, will be the sum or difference of the antiderivatives. Now, what will happen here when you do this, and this is what typically happens with integrals or antiderivatives, we'll write capital F of x plus its constant plus or minus capital G of x plus its constant. We'll call that C2. And what usually will happen is we'll combine these to be f of x plus capital G of x plus c, where this c is c1 plus c2. It's a very common thing when you're working with integrals. Some questions about that? So let me do an example with these. So let's find the antiderivative of 2x plus 6 cosine of x plus 1 over square root 1 minus x squared dx, for the antiderivative of this. And what we've been told is we can divide and conquer. So it'll be the integral of 2x dx plus the integral of 6 cosine of x dx plus the integral of 1 over the square root 1 minus x squared dx. Now, taking a look, we know the antiderivative of 2x, x squared. Now, this one, we've got 6 cosine x. So this 6, we can have it pop outside the antiderivative and then do the antiderivative of cosine x. And we know what that is. That's sine. And we know the antiderivative of this is sine inverse. So what we'll get, x squared plus C1 plus 6 times the antiderivative of cosine x dx plus the sine inverse of x plus C2. So you have x squared plus C1 plus 6 times sine of x plus C3 plus sine inverse of x plus C2. And so this will become x squared plus 6 sine of x plus sine inverse of x plus c, and c is c1 plus c2, excuse me, plus c3. But that's going to be our answer. So any questions about that? So that's the setup for antiderivatives. What it really is just knowing your derivative chart. And you just sort of guess. Well, you don't guess. You work backwards. If the derivative of this gives you that, then the antiderivative of this is where you started from. And you always add that plus c, because the derivative of anything plus a constant is going to give you the same result regardless of the value of that constant, whether it's 0 or the constant isn't there, or -5 or pi over 2 or anything like that. So that's an introduction to antiderivatives. Now it's time to get really into the core of things with these antiderivatives. We're going to start from a totally different angle. We're going to talk about areas and finite sums. So what we're going to do is this. We're going to estimate areas using rectangles. We're going to do this. We're going to work with basically the same function over the same interval in this section. But we're looking for areas that might not be canonical. These are areas that the Greeks really didn't calculate, or ancient Indians, or the ancient Chinese writers. These are areas that they don't seem to be very, how do you say, popular in ancient mathematics. It's not to say someone didn't try to come up with it. Maybe someone in one of the Mayan civilizations, sub-Saharan Africa, but it's something that you don't start seeing the formulas for it until relatively recently. So we're going to be using the formulas that have survived. And this was the idea that we use in calculus. And at first, it might seem a little sloppy. Like, we're kind of saying, well, this is good enough. But we're going to try to improve on this method. But we're basically saying this area is approximately that area. And so we're going to look at first 3 different sums, 3 different ways of doing this. So any questions about that? All right. So this might have been something ancient peoples had come up with, but this is the method that sort of survived. There is one method that survived. There's something called the method of exhaustion. I think it was used to come up with the area of a circle, sort of along these lines, but we're going to study this function. So first off, we're going to talk about what are called lower sums. Now you might be wondering, what the heck does this have to do with indefinite integrals? It has something to do with them, and it has to do with that dx that we saw. So if we graph this, say this is 1, this is 1. Here, I need to make this a little bit. So I'm going to erase this here so I have room to experiment with the mathematics here. So we're going to work on this interval. There we have 1/2, 3/4, and 1/4. And again, this is this function, y equals 1 minus x squared. And we're looking at it on the interval 0, 1. So when we're going to talk about a lower sum, we're going to use rectangles that are underneath on the inside of the arc. And so what we're going to do, we're going to add up. And this one is just kind of, it's just flat. Don't get a rectangle here at all. It's kind of a stinker. But we're going to approximate our area using these rectangles, and this one has a height of 0. So this point here is 1/4 and 15/16. That's kind of hard to see, let me know. But 1/4 and 15/16. This one is 1/2 and 3/4. So the y value is 15/16. Y value is 3/4. And this one, when x is 3/4, the location on this curve, the y value is 16. We're dropping. So the y value is the height of these rectangles. And then each one has a width of 1/4. So this would have a 1 and a 0. So a rectangle area will be 1/4 times the y coordinate. Y coordinate gives the height, and each of these has a base of 1/4. So that means the area using this lower sum is 1/4 times 15/16, 1/4 times 3/4. 1/4. Again, that's the base of this rectangle is 1/4. The height, 7/16. And then 1/4 by 0. And if you round this bit, what we'll get is approximately 0.3125. So that's the lower sum. Now, the actual area here is 2/3, or 0.6 repeating, or 0.667. So this is off. It's not a great approximation. But let's try a different type of sum. So any questions about, and again, if I'm going too fast, let me know. All right. The upper sum. And again, same function. Same partition. Now this time, we're gonna go with the highest y value we can come up with. So for this rectangle, the highest y value this rectangle could possibly have would be 1. For this next rectangle will be here. We'll take a look at what those actually are. This rectangle, and pardon any artistic license, we have this. And for this one, it doesn't have a height of 0 this time. It's going to have this. So now we're going to approximate using rectangles that sort of overshoot the mark. The ones that we had before were too small. These are just a bit too big. And so we're going to use this time, backwards here, these points. So now we have 3/4 and 7/16, like we did before. And then we have 1/2 and 3/4. 1/4. I'll have to erase this part for mine. 1/4. 15/16. And then this one, though, we have 0 and 1. Now, when we approximate the area, again, base times height, base times height. And the base is always 1/4 in this case. So the area is approximately 1/4 times 1 for the first rectangle, 1/4 times 15/16, 1/4 times 3/4, and 1/4 times 7/16. And this one, we overshoot, we get 0.78125. So there's one more kind of sum that we can use, and it's called the midpoint rule. So once again, we're going to divide that same function on that same interval and give it a partition. We're going to divide this a little more finely. We're going to locate the midpoints between these hashes. So this here, the midpoint, 1/8. This one here, 3/8. This one here, 5/8. This one here, 7/8. So now when we construct our rectangles, we're going to have the height of the rectangle evaluated at these midpoints. So here we'll get 1/8 and 63 over 64. For this one, so we kind of overshoot a little bit, we undershoot also. This will be 3/8. Ooh, it's hard to see. And 55 over 64. So again, it overshoots and undershoots. This one is 5/8. If you're having a hard time seeing this, just let me know. 5/8, 39 over 64. And then this one, 7/8, 15 over 64. And so once again, we're going to approximate this area using this type of sum. So any questions about that? Here, I'll do the addition. We'll erase these here. A little more room. So in this case, the area, for the lower sum, we undershot. For the upper sum, we overshot. We get 1/4 times 63 over 64 plus 1/4 55 over 64 plus 1/4 39 over 64 plus 1/4. Again, base times height is what I'm doing. 15 over 64. And that is approximately, now check this out, 0.67. Here, I'll give you a little more room. This is approximately 0.671875. So this method actually got us really, really close, which was really cool. Now, the actual value is 2/3, which is 0.6 repeating. So this got us pretty darn close. So you can estimate these areas using rectangles somewhat accurately. Somewhat accurately, you can do that. And there's a trick to this. We'll talk about it at the very end. So any questions? All right. So we're going to look at some applications. And the first one is what's called distance traveled. And the idea is this. Distance, is velocity times time. Distance is velocity multiplied by time. So for example, let's say this is time, and that's velocity. So let's say your velocity is 7 meters per second. Again, this is a physics thing. We always do things in meters. And we're going to travel this for 10 seconds. Travel at this speed. So that means our velocity is going to be constant. And then we're going to stop. Well, the distance in this case here, velocity, v, is a height. Time, t, is a width. So the distance, which is velocity times time, is the area under the velocity. And I'm going to call it a curve. It's a pretty plain curve. It's just a horizontal line, but what we're going to get, the area 10 by 7, that means 10 times 7. The distance is going to be 70 meters. Or we can check this computationally. Okay, 70 meters. So we can think, this is a weird thing to think about, but if you have a velocity axis and a time axis, then distance is the area between the velocity curve and the t-axis. That's really weird, I'll admit. But I mean, it worked out really nice, no trouble here. But let's make it trickier. And this is where calculus comes in. Let's suppose the velocity is a little trickier. So what is distance traveled for this velocity curve? See, our velocity curve does this. This is t, and this is v. And so this distance is the area. Distance is the area underneath this curve. So what can we do? This is where calculus comes in. What we can do, we can take this velocity curve. So we're going to divide this into 4 sub-intervals. Use a midpoint approximation. The midpoint of each of these rectangles. We'll call this midpoint C1, C2, C3, C4. And then each rectangle is going to have the same width, delta t. We've divided this interval evenly. So again, the approximate area will be the sum of the areas of each of these rectangles. So this rectangle, its top has coordinate of C4, F of C4. This one, C3, F of C3. this one, C2, f of C2, and then this one would be C1, F, C1. Now this is pretty abstract, I'll admit. But the height of these rectangles, again, it's the y-coordinate. The height is the y-coordinate. The height, y-coordinate. The height, the y-coordinate. So the distance in this case, which is the same as the area, will be delta t times f of C1 plus delta t times f of C2. And again, that's the area. Base times height. Base times height. Base times height plus base times height. So questions about that? I'm going to do an example here. It's a little more hands-on. Something not so abstract. All right. So let's do a hands-on, something with some numbers we can calculate. So let's say we have something like this. And again, the vertical axis is miles per hour. And the horizontal axis is time. And let's say our velocity curve, let's say at 1 hour or at 23 hours will be at 40, 5 hours will be at 10, 7 hours will be at 50. So our velocity is kind of all over the place. So we have a velocity curve doing something like this. It's just running all over. So this might represent like a lot of stop and go traffic. So again, I'm going to use 4 partitions. So I'm going to use this as my midpoint. Excuse me. And that's our rectangle. For the first one, here's the second rectangle. We'll do this. Third rectangle, we'll do that. And then for the fourth rectangle, we'll use this. So we're going to approximate. Again, this is velocity and time. So velocity times time gives us distance. So in this case, the distance is approximately, now let's look at the base. The base is each of these rectangles. I better get some time here. Let's say this is hours. It's going to be 2 hours, delta t of 2 hours, delta t of 2 hours, delta t of 2 hours. So this means you have a distance of 2. The height of this first rectangle is 20, plus a rectangle with a base of 2, a height of 40, plus a base of 2 and a height of 10, a base of 2 and a height of 50. And what we get is 240 miles. So questions about that? So that's the idea. How this is a very powerful use of calculus. You actually use this a lot when you're working with the concept of work, where you have force times distance, have like distance here and force here, and the force is changing over distance. Like you could be running into obstacles as you go, friction and things like that. So another application, total distance traveled. We're going to get more into this later. Right now, we're sort of limiting ourselves to curves that are positive, like they never dip below the x-axis, or we don't try to estimate the area for a part of the function that dips below the x-axis. We will deal with that later. This is kind of it. So let's say you're looking at distances. So you're going to travel from Roswell to Artesia. So you go south, you hit Artesia, that's about 40 miles. And then you're going to drive back up. Again, 40 miles. So at the end of your trip, what's your displacement? So the displacement, well, you stopped where you started. You just did a big circle. So you're back to where you started. So that's 0 miles. You're 0 miles away from where you started at the end of the trip, because you're going to start here, go here, and then this is where you end your trip. But then distance traveled, that's a total of 80 miles. So displacement at the end of your trip and distance traveled at the end of your trip are two different things. Now, let's suppose you've got this. The speed limit, 65. Between Artesia and Roswell, 65. So let's say the velocity is 65 miles per hour. And the time it takes, it's about 8/13 of an hour, a fraction of an hour. So the way we can think of it is when you go from Roswell to Artesia, you're heading out from initial position 0. So we'll give this a positive velocity. But then when you go from Artesia to Roswell, you're going backwards, essentially. So we're going to call that negative 65 miles per hour. Now, using the fact that distance is velocity times time, we can calculate your displacement as the sum of the distances. So 65. So let me do this. We'll do time, 8/13, that's our delta t, times velocity. And that gets us to Artesia. And then we have time times the other velocity. Well, this will give us 40 plus negative 40, or 0. Now, that's displacement or distance traveled. What we want is total distance traveled in this application. So total distance traveled we're going to use absolute values on the velocities. We use absolute values on the velocities. And so what that gives us total distance traveled will be our delta t times the velocity plus our delta t times the velocity. And this will come out to 40 plus 40 is equal to 80. And so that's how we guarantee. That's how we guarantee getting that total distance traveled. And the issue here is that we're going to start dealing with velocity functions not too far from now, where the velocity is going to dip below the t-axis. That means we're traveling backwards. And that's going to be something that we're going to want to be careful of. When that happens, we're going to use absolute values. So in general, the total distance traveled will be delta t times the absolute value of C1 plus delta t times the absolute value of the velocity, say at C2, plus, and this means we keep going, just keep adding on these terms. But we won't get quite so abstract just yet. We'll just keep it to 4. And that, if we use, say, 4 rectangles, that's what we would get. Questions about that? So the last application with this to talk about is going to be this. It's the average of a non-negative continuous function. So we're going to start with a situation like this. I'll partition this. Call this x1, x2, x3, and x4. This needs to be a little more in the middle. And let's say these are divided evenly. Like this is delta x. It's all the same width, delta x. And so we're going to take a look. Call this V1. V2. V3. And V4. So what we're going to do, we're going to use these four values to come up with an average value of this function from 0 to x4. So the average will be V1 plus, let me get a little more room. V1 plus V2 plus V3 plus V4 over 4. So what we can do, we can multiply top and bottom by delta x. Just serve an algebra trick. We can do this. Why not? Multiply top and bottom by the same thing. And so if we distribute, we'll get delta x times V1 plus delta x times V2 plus delta x V3 plus delta x V4. And this 4 times delta x, this is the length of the interval b minus a. So if you want to go back, this would help make a little more sense. If you go back to your picture of our function, you have x1, x2, x3, x4. This is something you'd want to add to your notes. So let's say, what did we have here? What did this look like? We have this, it drops down roughly, comes up, and then drops. Call x4b, and then here at the end of the interval, that's going to be a. So you can call x4a in the beginning of this. I'm sorry, x4 is b, the beginning. Let's call that a. And so what b minus a gives us is the length of this interval. And that length is, this is a delta x in here. If you look on your graph in your notes, 1, 2, 3, 4 delta x's. So 4 times delta x is the length of this interval. The length of this interval is b minus a. Give you a few seconds to update your notes with the b and the a there. All right. So going back, that's why 4 times delta x is b minus a. So what this lets us do, this here is an estimate between of the area between the curve and the x-axis. So this is the estimate of area under, in this case, instead of v of t, it's v of x, changed to variable, divided by b minus a. Questions about that? So let me do an example. So find the average value of y equals 1 minus x squared on 0, comma 1. Now, we know this from before. We could use the midpoint estimate at the beginning of class. So we know the area is approximately 0.67185. So that's when we did this estimation. Using the midpoint approach. Like so. So using the midpoint approach, we got this is an estimate of the area. So to find the average, we're going to take this estimate of the area and divide by the length of the interval. So the average is approximately the estimate of the area divided by b minus a, which will be 0.67185 divided by 1 minus 0, and that just comes out to 0.67185. questions about that? So the last thing to mention, and you've seen me do this for the whole lecture, but I've been only using 4 rectangles. We can improve our estimate of the area by increasing the number of narrower rectangles. And we're going to get into this in the next section. We're going to start getting into this a little bit. You'll actually see how we can use this technique to get that actual value of 2/3. So what we've done today is we've worked with this estimation. And this is when we have number of rectangles is equal to 4. But we can improve this. We'll have less misses, less overshoots, less undershoots for this area. If we use more narrower rectangles. So it's a better fit. And so this is where the calculus part comes in. With calculus, we've been toying with infinities or maybe making things smaller and smaller. But if we made these rectangles infinitely narrow, we could fit, in principle, infinitely many in this area. So here the number of rectangles in approaches infinity. And this is where we're going with antiderivatives, believe it or not. We'll talk more about this later. But that's the end of section 5.1. We've done 4.8 and 5.1 today. We'll be looking at 5.2, 5.3. 5.3 is kind of a long one. We might not get out of there. So we'll see. We'll probably at least 5.2, 5.3 on Wednesday. Again, I'm holding back on the quizzes for now. I will put a quiz out tonight. I'm going to send one out tonight. But slowing up just to kind of give you some time to work on that homework. Make sure you're feeling pretty confident about derivatives. And then we'll move on from there. I'll start putting out more quizzes. So that's going to be it for today. We're getting into indefinite integrals. And if you have any questions, let me know.